so that we can preview these lessons sometime back or later on. And also you allow me to share with you what is on the screen. What is on the screen. And let me see. Okay. So this is what is on the screen. I know you have downloaded this book and we are looking at modern physics. So I'll scroll where we have modern physics somewhere here. And that's where we stopped last time. We looked at what we call the time-based switch and the time-base, and both things, two of those things are different. The time-based switch, is connected to the X plate, and it is used to move the bright spot horizontally. So that is the switch that is connected to the X plate. Now, what you should know is that always the time base is connected to the X plate. The time base is connected to the X plate. So a time base is the time base. That's where we stopped. First of all, allow me to greet members. There is Kabami, good morning. Esther, good morning, everyone. You can unmute in case your background is clear and you want to say something. So the time base is a special electrical circuit. If I may zoom in there, so that we use on this side. This. So a time base is an electrical circuit. It is a special electrical circuit which generates a sawtooth voltage. And this time base is always connected to the X plates. So you should know the difference. Where is the time base connected? The time base is connected to the X plate, and through that time base switch, and this time base, it will generate a sawtooth voltage. Now, why do we say a sawtooth voltage? Because this kind of voltage, or this kind of PD, when I talk about voltage, I'm talking about PD. So the PD means potential difference. Potential what? Difference. So potential difference, where does it come from? If you have a dry cell, it has the positive side and the negative side. So the positive is at a positive potential and the negative is at a negative potential. So the potential difference between those two sides, or those two terminals, or those two plates, is what we call the potential difference, or the voltage. So that is the potential difference. And later on, when we are studying electricity, we shall be able to define what potential difference is. So the PD, or the voltage of a sawtooth voltage, appears in such a way that it rises steadily and then falls suddenly. All of a sudden, it falls down to zero. So rapidly, it changes to zero. But when it is raising, it raises steadily. Steadily, that's a straight line that I will show. So time base, first of all, we can define it, that is a special electrical what? Circuit. The special electrical circuit which generates a sawtooth voltage. Full stop. That's the time base. Electrical circuit that generates a sawtooth voltage. Now you should know that the time base is connected to the X plates. So the time base can be on or the time base can be off. So when the time base is connected to the X plates, there is always a spot of the electrons that will be seen on the screen. And this spot, we shall see it as a linear sweep running from the left to the right, moving from the left to the right. So you should know that always when we have the time base on, the time base connected to the X plates, it will cause the electron beam to move from the left to the right. And this is what we call the linear sweep. Is what we call the linear what? The linear sweep. So let me give you only 15 seconds, and I want you to come up with a definition of what
Short definition.
Short definition.
Okay, members. Now, have you come up with a definition of linear sweep? Yes. What did you understand by the term linear sweep? If someone may ask you, what do you understand by the term linear sweep? Anyone who can try? Members, are you there? Members, are you there?
Yes, teacher.
Anyone who can try what linear sweep is? What do you understand by the term linear sweep?
This is when the time base is connected to the X planes and causes a spot to move from left to right.
This is what? This is when? Yes, what do you understand by the term linear sweep? Maya, I've increased on the volume. What do you understand by the term linear sweep?
This is when the time base is connected.
The time base is connected to what? Time base is connected
It's
to
connected to the X plates and causes the spot of electron beam to move across the screen from left to right.
So we can say that linear sweep is the movement of the electron beam or of the electron spot from left to right when the time base is connected to the X plate. Are we together?
X plate.
Yes, is the steady movement, or steady motion, can say steady motion of the electron beam from left to right when the time base is connected to the X plates. That's linear sweep. I mean, yes, that's linear sweep. So during that time, the electrons, they will be made in such a way that they are moving from left to right. And that is the point where we have a steady rise in the voltage, So when we notice that there is change in the direction of the electron beam, then it means that that motion is what we call the linear sweep. So it means that the voltage is increasing steadily. And then what do we call the other part where the voltage rapidly returns or falls to zero? That point is what we call the flyback. Cynthia, can you stop that? That's what we call the flyback. So the flyback is that motion of the electron beam when it steadily falls back to zero when the time base is connected to the X plates. So that time back is that time for which the electron beam rapidly falls to zero when the time base is connected to the X plate. So we can say flyback. So first fix my camera here. Okay, flyback. Let us look at flyback. We shall be able to see all the things in the video, but flyback first. Let us first have the notes. Flyback. This is the motion of the bright spot. Is the motion of the electron beam when it rapidly falls to zero when the time base is connected to the X plates. So that is the time, that is the flyback. This flyback takes place in a shortest time. It is very hard to notice that time. So this is where we have the linear sweep from left to right. You know, when you are moving from the negative to the positive is on the right and the negative is on the left. So from left is negative and then positive to the right. So this is left to right and then it falls back. And again, left to right and then it falls back. So at the end, this kind of time base, when it is connected to the X plate, it will form what we call a sawtooth voltage. In that kind of form, a sawtooth voltage. So you go ahead and draw that sawtooth voltage, and you should illustrate how it looks like. So we have this PD. This side we have, here we have the PD. Okay, and the PD is, this is the PD. This is the PD. So units are there. It should be measured in volts. This is 0. Side is positive. The side is negative. Side is negative. Okay. Zoom in there a little wire and you see clearly. So we are going to draw the first one, which is the, we are going to draw the linear sweep from the negative to the positive. So this distance, which is here, must be the same. So if that is 1.8, this should be also 1.8 somewhere here. So I'll have my negative this side. Put my negative here, such that we have this. Okay, like that. Then afterwards, it falls to 0 rapidly. This is a straight line. Yeah. And then we have it again, that kind of form. Okay. And then it falls back to 0 again. It falls to 0, then returns to negative, like that. This should be of the same, they must be parallel. These lines should be parallel, like that. And then in that nature, like that. So we shall have a linear sweep and we shall have the fly back in that direction, like that. And now this one, this is what we call the time in seconds. So the time that is taken for this voltage to fall back to 0 is this time which is here. So I don't know what's the difference between the time which is here. It is very small. It's very small here. It's very small. It may be like microseconds. The time which is in between. When I say in between, I've drawn a line. If I may use another paper here, I've drawn a line like this, and I've drawn the fly back like that. So this is the fly back here. This one is the fly back. But if you may magnify into this fly back, so you get something which is such that the time that is there in between is very small. That's why we just drew it as a straight line here to show that the time that is in between the starting point here, the initial and the final, they are at the same point here. So it means that the time that is taken here is very small, compared to this one. For this one, the time that is taken, we shall take this time from here up to this time which is here. So the time here is quite large for the linear sweep, but for the fly back, the time is very small because it appears just like a straight line. So in most cases, it is very hard for us to notice the time back. The fly back. It's very hard for us to notice the fly back on the CRO. The reason is that during that time, the grid, its negative potential is increased. And if its negative potential is increased, it means that a few number of electrons are able to reach the fluorescent screen. A few number of electrons are able to reach the fluorescent screen. That means that during the fly back, we expect the brightness of the spot to reduce because the grid automatically adjusts its negative potential to a high value such that most of the electrons are repelled back into the cathode and just a few are allowed to go through the anode to the fluorescent screen. That means that the fluorescent screen, we shall see, we may not see this kind of electron moving from one point to another during the flyback because the electrons have been reduced. The number of electrons which are reaching have been reduced. So that's what they are saying, that during the flyback, the control grid is automatically made more negative, thereby suppressing the brightness of the spot. So we said that the grid is used to regulate the brightness of the screen by regulating the number of electrons which are able to reach that fluorescent screen. So we looked at how the grid does that if it is made more negative, then it means that less electrons are allowed to go through the grid and the anode and to reach the screen. That means that the brightness is likely to reduce. So that's what they are saying, that if it's made more negative, thereby it will suppress the brightness of the spot. So that's what we call the time base. But you should know that the time base, for us to understand very well how a CRO works, we should have the fluorescent screen. And the fluorescent screen is coated with a zinc sulfide, or it is coated with graphite, so that it can absorb the energy of the electrons, and we can see the electrons in the form of a bright spot on the screen. So the inner wall, I don't know whether you have those screens, those TVs of a long time ago, but for me, I used to dismantle some of those TVs at home. We had one and it was old, so I dismantled it to see what is happening inside, what is inside. And I found out that inside that screen is coated with a certain powder, and that powder was graphite. So graphite is coated in the inner walls of the cathode ray tube to trap all the stray electrons emitted from the electron, and this makes the potential in that region uniform. So graphite will absorb, it will trap them, it will absorb. The reason is that we don't want to have electrons being scattered all inside the tube, like how we have, last time we were looking at reflection of light, and you looked at a pinhole camera and you say that it is blackened inside to prevent multiple reflections within that camera. So even here, the CRO is coated with graphite in order to prevent those kind of maybe stray electrons, which may keep on bouncing from one surface of the inside wall of the tube to another surface. So graphite, what it will do, it will absorb all those stray electrons. The word stray electrons means that those scattered electrons which are moving in different directions, such that we don't have electrons which are just moving within the cathode ray tube and they are not moving in a straight line. Previously, remember that we say that one of the properties of cathode rays is that cathode rays travel in a straight line. So we should make them to travel in a straight line such that they are able to reach on the fluorescent screen. Now, that should take us to this other part here, the action of the CRO. And the action of a CRO, here we are going to look at the advantages or the uses of the CRO, and how a CRO is how do we study the waveform of the CRO depending on the time base and what is on the Y plate. Now you should know that in a cathode ray oscilloscope, always want to measure. For instance, I can give you one advantage or one use of a CRO is that a CRO or a cathode ray oscilloscope, it is used to measure the voltage, and whatever you want to measure, for instance, the voltage can be of a dry cell, the voltage can be of an accumulator, the voltage can be of a generator, anything a CRO can use to measure voltage, or it can be the voltage of a photocell that we looked at previously when we were looking at photoelectric effect. So the cathode ray oscilloscope has got what we call the fluorescent screen, and we have circles which are here. These circles will represent what appears on the fluorescent screen. And you should know that what you want to measure, if you want to measure the voltage, then the voltage is always connected on the Y plates. So whatever you want to measure, you want to measure current, you want to measure voltage, you want to measure frequency, everything that you want to measure is connected to the Y plates. And then on the X plates, we connect what we call the, let me ask you that question. What do we connect on the X plates? If you have been attending this lesson for the last 30 seconds. What do you connect on the X plates? For the last, yes, Esther?
Time base.
Correct. We connect the time base on the X plates. So we are going to look at the wave nature of this kind of cathode ray oscilloscope with our video, which I've already prepared for you. So first of all, let us look at time base off. Time base off. So if the time base is off, it means that there is nothing that you have connected on the X plate. So the time base, remember, it is an electrical circuit connected on the X plate that will give us a sawtooth voltage. So it means that if time base off, then it means that we have not connected the X plate to the time base. So the X plate is empty, nothing is connected on it. And then they are saying that now if you have the AC signal, now if you don't connect to the time base, but if you don't connect to the time base on the X plate, but you connect the AC. AC is the alternating current. You connect the AC signal to the X plates. This is what we are likely to see. So we shall see a horizontal line, and this line is due to the electron moving from one side to another, one side from left to right, from left to right, from left to right. So let us see that. See if I can have that. Wow. Time base here. Put it where? There. Okay. Members, are you there? Are you there? People, are you there?
Yes.
Okay, so let us see what this gentleman is trying to tell us. We are looking at the AC connected to the X plates. Let us first see this one. Of course, not that. So skip this video and we shall first go back. Okay, let me first stop this. So this is what we call the CRO, and that is the screen. So this is just a kind of an animated image just to show you. I think you can see very well. Maybe I can just put that full screen. And I can also increase on the so the cathode ray has got the Y gain and the time base. So this is what we call the time base here, and this is what we call the Y gain. Here is what we call the grid. So it is indicated here that it is brightness. I want to increase on the quality of this image, but I think It has only 480 pixels. So now whatever I want to connect to, we connect it to the Y plate. So the Y gain, it means that you are connecting something on the Y plate, on the Y plate. So let me show you something here on page, on this point here, somewhere here. So when we put the voltage across the X plates, when you put the voltage across the X plates, this is likely what we are going to see. We are going to see something which is like that. That is an S on the X plate. So we shall have this horizontal line. What does this one mean? It means that the electrons are moving from left to right, from left to right, from left to right. So those are the electrons. That's how they'll be moving from left to right. And you can see this is the linear sweep. That is the linear sweep. And then that is the flyback, which goes back in the shortest time. So it looks like a horizontal line, a horizontal line. So that's the first part where we have, the SC connected to the X plates, and we shall have electrons moving from left to right in that kind of form. And what we shall see just a straight line. Why? Because the flyback takes a short time, but we shall be able to see just a straight line, a straight line on the screen. So note that one very well when we see our notes here. So when you go back to our notes, this is what they were talking about, that the horizontal line at the center when the SC is connected to the X plates. That is it. Okay, now the other one is, I know you are following. I know everyone is following very well. So the other one is when the time base is off. So the time base is off. If the time base is off, it means there is nothing connected. We have not connected the time base on the X plate, but we have connected something else. So in the first one, we connected the X plates with an SC. That is what we got. Now this time the time base is off, and if we connect SC on the Y plates, this is what we are going to have. This is what we are going to have. So let me show you that again. We are going to see a vertical line when we connect the SC on the Y plates. So let me look for 456. Okay. So somewhere there, so we shall apply the SC. Now let's say this is the SC here, which is connected to the Y plate. And then when we see, that's how the electron will be moving up and down, up and down, up and down, up and down. So what are we going to see on the screen? We are going to see a straight line, a vertical line, which is straight in the center. So it means that when the S is connected to the Y plates, we shall have a straight line or a vertical line. So that's the behavior of the electrons within, be moving up and down, that form. Okay. All right, so let us go back and we see the notes again, what they are telling us. Okay, yeah. So the other one is the time base is on. Now this time we shall connect the time base on the X plate, and we shall put the SC signal or the SC current or the SC voltage on the Y plates. And what we shall see, we shall get a sinusoidal wave. Let me ask someone here to give me the pronunciation of that word. When you are my best friend there, I know, and the rest are also my best friends. Now I'm asking you, Wendy, how do we call this word? It is read as Suni what? Suni what? Now, if at all you have not traveled to China, okay, you don't need to, Cynthia, you don't need to first travel to China. Are we together? For you to pronounce that word?
Yes.
Sunisoido. Is it okay? You just have Sunisoido. All right, it is Sunisoido because it is in the form of a sine curve. Remember when you're looking at trigonometry, when you're still at school here, we looked at cosine, we looked at tangent, we looked at different things. So this is sinusoidal because it is in form of a sinusoidal, a sine curve. So members, when we come back, we shall be able to see how this wave looks like on a CRO, and also prepare your questions to fire me, and also I'll fire you. Okay? Is it okay?
Yes.
Okay. So you come back, you log in very fast, and then you join very fast.